Okay, next is our last presentation for Ethernet Tech Day. The last presentation is a topology discovery feature for 10BASE-T1S multi-drop. Speaker is Mr. Piergiorgio Beruto from the Onsemi. So please, on stage.
Thank you. Okay, so thank you for the kind introduction. First of all, this is really my first time visiting this beautiful country, and I would really like to thank you all for the very welcome I received, so thank you. Allow me to introduce myself. My name is Piergiorgio Beruto. I'm employed by Onsemi as Principal System Engineer for Ethernet products. I've been part of the IEEE for 5 years now, and where I was the major contributor for the 802.3 CG group, and especially I'm basically the inventor for the 10BASE-T1S architecture and the PLC reconciliation sublayer. But I'm here today to talk about a new feature for 10BASE-T1S, which is called Topology Discovery. So Topology Discovery is a feature that allows you to measure the physical distance of two nodes on a on a multi-drop network, which is also called a mixing segment in the IEEE 802.3 terminology. So in this presentation, I will first go through some examples to better explain what kind of problem we are trying to solve with this technology. I will then give you some insights on how this topology discovery feature works, and highlighting the pros and the limitations of it. And eventually, I will basically go to some measurements and results that we obtain using currently available implementations in silicon. So maybe just a bit of background to better frame the problem. So since 1990s, well, Ethernet was mainly driven by the need of high-speed point-to-point links, mainly driven by the telecom industry, as we all know. And for this reason, multi-drop networks were kind of abandoned since then. However, with the rise of automotive Ethernet and Industry 4.0, basically drove the needs for having, as we have seen in these presentations before mine, basically full IP networks and service-oriented architectures, which push Ethernet further down to the edge of the network, well, for instance, where your sensors and actuators are located. And by the way, this is a very sensible area of your application because it becomes very cost and power sensitive. And this is where 10BASE-T1S was invented, and it sort of resurrected multi-drop back to the Ethernet world. And the reason for that is well known from other IVN technologies like CAN. So with multi-drop, you have one single pair cable connecting multiple devices on the same mixing segment. You are using only one PHY per device, and therefore you do not need large switches or gateways to bridge to other IVN technologies. And in addition to that, you have the PLC reconciliation sublayer, which further adds some performance to your link. So all of this translates into a big saving in system costs and power consumption compared to point-to-point. However, with multi-drop, we are also bringing back, let me say, some new old challenges. For instance, you want to identify the nodes that are plugged to your multi-drop network. And for the purpose, for example, of assigning IDs and application roles, like IP numbers, PLC IDs, and even MAC addresses. So in a point-to-point scenario, you can usually do this easily by knowing to which port your device is connected to. But what about multi-drop, since we are eliminating the needs of gateways? So this is exactly where topology discovery can be useful. Okay, so let me maybe start from very basic examples here. So one is, just imagine you have your car being assembled and you want to install radars on the same bus. And ideally, what you would like to do is just take a radar, pick it out of the box without any pre-configuration and without the need of any hardware settings. You just want to pick that thing, plug it to the right spot in your car, and then let some central ECU, by knowing where the device has been connected to, assign the IDs and the proper configuration that you may need for that device. So the same example applies as well for the car being serviced. Of course, if you want to replace a part or maybe just upgrade your car, ideally, ideally you would like to, again, just replace your part, picking a new part out of the box. Then, oops, then press a button, and that's it, without spending more time. That would avoid, of course, error-prone procedures that you have to do manually, which translates into a saving your time and therefore your money. So, looking at existing solutions for solving this problem, we already talked about point-to-point. So if you have a point-to-point architecture, obviously, as we said, you can just work out which port your device is connected to, and that would help you in identifying the topology. However, you lose the advantage of multi-drop in this case, and of the lower cost of T1S. Another solution is basically based on a daisy chain of devices which are connected together and interrupted by switches, by real switches. So in this scenario, one central unit in principle can basically bring up one device at a time and closing the switch sequentially, so you can know which device comes first. Although in this solution you have two problems. So one is, of course, you pay the additional complexity of the switch, which must be controlled. And also, from an implementation perspective, that's not very easy to achieve sometimes, because if you are in a harsh EMC environment, which is typical for automotive, then sometimes switches create problems being in line on the bus. And of course, there exist some other proprietary solutions which typically require some additional hardware and software, and by definition, they are not interoperable. Therefore, this is typically not desired. So how this will look like instead using a topology discovery for 10BASE-T1S. So the solution itself is similar to the daisy chain solution that I mentioned before. However, you do not have the additional complexity of the switches and the additional costs as well. So it works without extra cables and without extra controls. The topology discovery can measure the position of the node with respect to one node that you choose as a reference with quite an high accuracy. That's less than plus minus 5 centimeters as an error. I will show you that later. And it is a full Ethernet solution. It will be standard, and therefore, even without using gateways or extra cables, it will just work. Another important thing to mention is that another advantage with respect to the switch solution is that you can have nodes not being plugged into some spots, and the system will still be able to work, and it will detect the next device even if some of those are not plugged in or maybe not working, something that you cannot have with the other solution. Okay, so hopefully I explained what's the problem we are trying to solve is, and I will give you some details on how this topology discovery works. So the first thing is, when talking about measuring distances, one may ask, well, why don't you use time domain reflectometry, which is a well-known technique to do this kind of measurement? So the answer to that is that, yeah, well, in principle, you could try to have maybe a node creating on purpose a short circuit on the bus, which, by the way, it's, again, not very easy in a harsh EMC environment to keep the switches really closed without creating weaknesses in the PHY. But even if we do that, the real problem is that on a mixing segment where you do not have a continuous transmission, rather each node will transmit as needed, you have changes in impedance, and these are mainly due from transitioning from the transmit state and the receive state of each node. And when you do that, you get a significant attenuation of the reflected pulse that you may be sending, which means you have a lower SNR. So this picture will basically tell you what I'm talking about. So if this is a pulse that you have been sending on the multi-drop bus, and you expect a strong reflection out of it, but instead, depending on your topology, you typically get some smaller step because of the reflected signal. And this leaves basically no margin to properly detect and recover this, the propagation delay, which basically translates into the distance that you are interested into. So this is why, with Topology Discovery, we decided to change the approach. So what we did is actually using what we call the transponder solution. That is, you have a node which you decide it's the reference node. You will ask each node in turn to go into topology discovery mode, and then the reference node will start sending out a pulse, a single pulse on the line, and this pulse will go to the measured node. It will traverse an internal delay line, which purpose is to have only one pulse at a time being present on the line. So it will basically swallow your pulse and repeat it back, right? In such a way, as you can see in the graphic, that you only have one pulse. And then back and forth. So if you measure basically the number of pulses that you receive within a specific time window that is known, you can basically work out the contribution or to the delay of the length of this cable. Of course, you also need to know exactly how much delay you have here and here, which can be controlled, but it has to be controlled in a very precise way. So we are talking about the picosecond range here. So for this reason, the idea is that you basically reuse the same mechanism, and you have a kind of calibration phase of this topology discovery, where a single node will transmit pulses and will receive the transmitted pulse closed on itself in a loop. So again, now the frequency of the pulses that have been transmitted here is proportional to this internal delay that you have. So a node on the network that is listening to your to these pulses can just measure the frequency in an easy way and measure, therefore, the contribution of this internal delay. So with that said, this is what the topology procedure would look like in a real example. So ideally, you have node number 0 that will start the internal delay measurement. Well, it may not, these 0, 1, 2, 3, they are not related to PLCA numbers, just to be precise. These are whatever numbers you decide to assign, just as an example. Okay, so let's say this is the reference node. The reference node will first measure its own internal delay. It will then ask, using a message, one of these nodes to enter topology discovery mode, and then it will ask the node to start the calibration phase. So node number 0 will measure the frequency of the pulses sent by node number 2 and work out the internal delay of node 2. And when this is done, the process can start of going for ping pong of the pulse between the two and measuring the actual distance. Knowing the internal delay of the two, knowing the number of pulses that you received in a specific time window, you can say exactly where this node is located. And so just to show you the results that we obtained using an existing implementation of this technology. Okay, so you want to consider this as a test setup. So here we have 8 nodes. These are 4 PHYs and 4 10BASE-T1S MAC PHYs connected using cables of different lengths. And we choose one of these nodes to be the reference node. And then this is a video showing a software that does all the, let's say, handshaking that I was describing before. So let me see if it starts. Yeah. So at this point in time, you have an unordered sequence of nodes starting the protocol, and boop, there you get exactly how many nodes you have on the network and which is the distance among all the nodes. So with that said, we can look into how this translates into our sensibility. Okay. So these small bars that you see here, they represent well, the measurement being repeated multiple times to see, basically to measure your repeatability. So you see that on a full, that is a 14-meter link, you have enough sensitivity to basically check where the nodes are located. And this error that you see in this table is the maximum deviation from the average value of each of these repeated measurements. So a value of 6 here really means that you have a plus minus 3 centimeter as an error. So just to zoom in a bit to see the actual accuracy that you can achieve, we decided to focus on these 2 nodes here, node 2 and 3, which are pretty close to each other, using this very short piece of cable that you can see here. And then this is the zoom in of the previous measurement. Okay. So you can clearly see that the repeatability here is in the range of this roughly 6, therefore plus minus 3 centimeter. And so the condition to distinguish this node from this node is really that, you know, considering the width of these bands here, you still have, you know, a greater than 0 margin here. So therefore, we would consider a safe value for your accuracy to be plus minus 5 centimeter to take some margin. Okay, and then we also made some tests by testing the overall linearity. Okay, so this is really a test made by inserting in a specific topology cables of different lengths between the very same nodes, putting those on this line, and again, it's the number is consistent. You always measure a deviation of less than 10 centimeters, that is plus minus 5. That actually was plus minus 3 dot something. Okay, and so as a takeaway from this presentation, maybe a short one. So topology discovery allows you to detect the position of nodes connected to them to a multi-drop bus. The idea is that you want to measure the distance between the nodes, and it allows you to do that with an accuracy of plus minus 5 centimeter now. One important thing to say is that it's been standardized in the Open Alliance TC4T group, and therefore we are going to guarantee interoperability of this solution. And of course, you can still keep the reduced cost because you don't need to add any hardware or software specifically for this to work. So it's flexible and scalable. You can add and remove nodes to your network dynamically. And I think one important thing to note is that, as you may know, 10BASE-T1S is defined to be available in 3 different flavors, at least in the Open Alliance. The classical MII PHY, the MAC PHY with an SPI interface, and a CAN-like solution that is called the PMD transceiver, that is this 3-pin interface device. So all of these 3 flavors of 10BASE-T1S support topology discovery. That's been proven by real measurements. And of course, it opens also the door for additional use cases. So for example, this technique can be used, so this is work in progress, but it can be used for detecting faults or any kind of problem you may have on the link, for example, missing terminations and cables that are bended and they create reflections and so on. Okay, so hopefully I'm in time. So I wish to thank you for the attention and to also thanks to my colleagues that contributed to this presentation, although they could not join us here today. Mr. Henri-Xavier Delacour and William Vosard. So thank you so much.
Okay, thank you, Mr. Beruto. It was very, very easy to understand your explanation, what topology discovery is. So do you have any questions to this presentation? Okay.
Hi, thank you for a nice presentation. I'm Shu Ishizuka at Toyota. I have one just simple question. How long does it take to complete the topology discovery?
Okay, that's a good question. Thank you. I didn't put the number here. So currently, the level of accuracy that you see here is obtained by integrating over a time window of roughly 1.2 milliseconds per node. Okay. And this number is configurable. You can increase it to increase the precision, or you can decrease it if you want to speed up and you get some less precision or some less immunity to noise. But that's tunable. We believe that 1.2 milliseconds is a reasonable number for the measurement. Of course, you have to add the time you need for handshaking, using some software protocol on top of it. So roughly you have to double that number, just as an order of magnitude.
That's fine. Thank you very much.
Yeah, you're very welcome.
Okay, any other questions? Okay, may I ask one question? So you said this topology discovery standardized openness in OpenAlliance TC14. What the status of the standardization?
Yes, so the status is pretty complete. So we got consensus on in the Open Alliance, and the draft will be out for review, very soon, probably next week. And then we just need some time for the IP review. That will be roughly a couple of months for the published version. But the draft is stable, is closed, and so therefore, people are already implementing, as we have seen also from other presentations.
Okay, thank you.
Yep.
Any other question? Nothing? So thank you, Mr. Beruto, for your nice presentation.
Yeah, thank you.